Thank you so much for the introduction. And hello, everyone. Today, I'm gonna talk about problem of sweeping polygons with a variable length line segment. And this is joint work with my advisor, Joe Mitchell, and with Valentin Polichuk. So the I will start with the definition of the problem. So given a polygon P, we want to sweep every point in this polygon using a line segment. And a point in the polygon is considered swept if it is touched by the segment at any point during the schedule. And the segment can be as small as a single point, and it can be as long as the diameter of the polygon. There's no constraint of the length. But we require that the segment must stay within P at all times, and this is what we call the unbreakable constraint. So the two endpoints of the segment have a maximum speed of 1, and the segments both of the endpoints start at the same location, which is a point on the boundary of the polygon, and they at the end they will go back to the beginning. And finally, the objective of the problem is for us to find the shortest sweeping schedule that sweep every point in the polygon as quickly as possible. So this can be seen as finding a static target in P. So any problem with any question about the problem? So the problem definition?
It
Yes.
has to start at a point and like grow.
Yeah, and then at the end they will go back.
So in some sense, are you trying to see how convex your shape is? Is it about like
Yeah, it's kind of like an estimation of the shape of the polygon. So before going into the details of the problem, I want to introduce some of the more related work. So first we have sweeping a polygon with a polygonal chain. So in this mechanism, there will be agents and they will form a polygonal chain going from the boundary of the polygon to the boundary of the polygon, which separate the polygon into two separate regions, one which was swept and one which is unswept. And then there's also a problem, the milling problem, where you sweep with a fixed radius disk. And then the more popular problem where you sweep everything with a visibility polygon, which is the Watchman-Rao problem. And then finally, we also have sweeping with a thin fast light. So among all these, I would argue that the first one is the more similar, the one that is the most similar to what I'm going to talk about. So here are some of the main results of the problem. So the problem is NP-hard even for a simple polygon. And for simple polygon, we have a constant factor approximation algorithm. And we also have a constant factor approximation for polygon with holes. And when you have more than one segment in the input, we also have constant factor approximation. So I will begin with the hardness of the problem. So given a simple polygon, the problem of compute the optimal sweeping schedule is NP-hard, even if the polygon is simple, X monotone, and orthogonal. So to see why it is hard, I will begin with a very simple but important lemma. So I will use this lemma again and again in the presentation. So to sweep every point in the polygon, you also need to sweep all of the convex vertices. But to sweep a convex vertex with this mechanism, we need at least one of the two endpoints of the segment to directly touch the convex vertex. But this is not true for reflex vertices, as you can see in this picture. So to prove that it is NP-hard, we use reduction from 3 partition, which says that if you give me 3m integers, which sum to ms, can I partition them into m triplets so that each of the triplets sum to exactly s. And what I will use to prove that it is NP-hard is the gadget that you can see on the right. So this gadget is a polygon and it's very thin. So the width, the horizontal width of the polygon is very, very close to 0. But so to see what's going on, I need to kind of expand it horizontally to see what's going on. So this is the gadget, but visually extract. So for this gadget, there will be something that we need to take a look at. On the top, we have these chimneys, and each of these have the height of xi/2, which correspond to the integers of the three partition instance. And on the right, we have the staircase, and between two steps of the staircase, the space between them, I mean, the distance between two steps will be exactly s, which is the sum of the triplet. So to see how does this polygon has to do with three partition, I want to introduce how does the segment sweep all of the chimneys. So let's say we have a segment color is blue here, and it's going to sweep this chimney of height xi/2. So what it will do is to extend in both directions. So the top endpoint will reach the top convex vertex of the chimney, and then the bottom endpoint at the same time will move down up in the same amount of length. And then the segment will move from the left to the right to sweep the chimney, and then finally get out to do something else. So as you can see, after all of this is done, the segment will gain a length of exactly almost about xi, not exact, but like almost xi. So with this, the gadget will work as follows. So the segment will begin at the top left corner of the polygon, which you can see as labeled by at the point labeled by S. And then it will travel from the left to the right and pick up the correct triplet of chimneys. So once it's pick up the correct triplet of chimneys to sweep, it will gain a length of exactly S, which means that it has just enough length to sweep the staircase on the right. So that's it for the gadget. So once this is done with the first step, it will go back to sweep another triplet and then go back to the right to sweep another step of the staircase, so on and so forth until it sweep everything. So remember that the width of the polygon is very, very thin. So the movement from the left to the right and reverse doesn't really matter. We only care about the vertical movement. So now that we know that the problem is NP-hard, we want to approximate it. So to approximate it, we need to figure out some kind of low bound for it. So this is the low bound that we use. So consider the TSP tour that visit all of the convex vertices of the polygon. Then the low bound say that the optimal solution has to be longer than or equal to a half of that tour. This is because if you consider the two endpoints of the segment from the beginning to the end, it has to be two tours that together visit all the convex vertices, and the union of these two tours cannot be shorter than the TSP tour of one agent going around the boundary to visit all the convex vertices. So that's why we get this low bound, which is opt is greater than or equal to a half of the perimeter of P. Yes?
Sorry, Kien, so the TSP is within the polygon, right?
Yeah, within the polygon. Yeah, I should have mentioned that, because if the TSP can go outside of the polygon, it's not true anymore. Yeah. So the half of the perimeter is the lower bound of the optimal solution. So what do we want to do with it? So our approximation algorithm works as follows. We partition the polygon into subpolygons. Each of the subpolygon is simple to sweep. So this is how we do it. I consider any core in the polygon. So in this figure, it will be the core E. Consider any core E. So we will compute the following things. First, we compute the histogram polygon with base edge E, which is the blue region that you can see. And then if you take a look at E, it will have two endpoints, W1 and W2. So we will then compute the left visibility polygon at W1, which is restricted to the left of the histogram polygon. And then the right and then we do the same for W2, which is the visibility polygon at W2, restricted to the right of the histogram polygon. And the final subpolygon in our partition will be the union of these three things. So, but as you can see, when we compute these this is a polygon, it will, as a side effect, introduces some shadow cores, as you can see with the E1, E2, E3, etc. So with this, we will also do the same thing to them. We will keep repeating, computing all these polygons until we cannot compute it anymore. And with this, in the dual, we will have a tree. So each vertex in the tree will be a subpolygon, and two vertices will be connected if they are adjacent in the original partition. So to sweep the original polygon, we will simply sweep the subpolygons one by one. And the order that we sweep the subpolygons will also be the order that we get when we travel around the tree in that first order. But to actually sweep each subpolygon, what we will do is first we will assume that the segment will start at the left vertex of E, which is W1, and then we will extend the segment, and then we rotate around W1 and move the segment from the left to the right, because this is a histogram polygon. So we move the segment from the left to the right while keeping it vertical, and finally rotate it clockwise again to sweep everything. And this kind of polygon is important because when we compute the partition, we introduces these cores, right? So we want to bound the core somewhat. And because of the computation of this polygon, we can say that the length of E is, so E, because E has a histogram polygon associated with it, so we know that the length of E is bounded by some portions of the perimeter of some portion of the boundary of the polygon, and E can never be longer than these portions. So, and these portions, the red ones, is they are charged only once. So the total length of all of these shadow cores in the partition will never be longer than the perimeter of the polygon. So for the full thing to work, we need the first polygon. So for the first polygon, we will simply use the visibility polygon at the default of the segment, and we will start computing the next polygons from there. So with our calculation, we can sweep everything with this partition in the time of at most 4 times perimeter of the polygon, and this is less than or equal to 8 times up. And this whole thing can be run in linear time, assume Chasez triangulation, because we can. This is very similar to Windows partitioning, which is also linear time. So this is an animation that I got after struggling with implementing this in Python. But so yeah, so it will have the schedule of a tree because this is the depth of search. So any question?
Do you have any better approximation over?
So right now, I think we suspect that it might have a p-task or something, but like we haven't really, we weren't able to come up with it. But like we expect it to be much better than 8 because I ran some experiments and with pseudo with simulated data, but it doesn't say a lot, but it never gets anywhere close to 8. So I think the even with this algorithm, the factor is much better than 8 already. But
So what's the worst example you guys have gotten so far?
the worst sample, I don't. So it would be something like 4 something, but I don't remember the polygon exactly. But yeah, it should be some 4.5 or 4.5. Yeah.
Do you have any lower bounds other than the perimeter?
The low, good question. Yeah, right now the only low bound that we get is it's only the perimeter. So
The TS, sorry.
go ahead.
So the TSP can be as bad as the perimeter only if the polygon is convex, right? That is the only thing I can think of. If the polygon has any reflex vertices, then the TSP toward of the convex vertices.
It is still the perimeter of the polygon, right? Because you have to write.
So if it's alternative.
Yeah, it is always the perimeter.
So maybe a star is the worst example. Like a convex vertex followed by a reflex vertex, followed by a convex vertex, something like that.
Yeah, that could be true, but I need to take a look at it.
I'm just curious that maybe you can approximate the TSP and get an idea, get the different lower bound.
That's true as well.
And one can imagine some really messy polygon because there's a big gap between the perimeter.
Yeah. Usually the TSP lower bound is never achievable in any kind of realistic polygon. It is only in a few of them that the TSP lower bound is actually true. So that was everything for a single segment in a simple polygon. So now I want to move on to a more generalized version, which a very nice extension. So here we have multiple segments. Now we don't only have one segment at the depot, we have k segments and their job is still the same. They sweep everything and then at the end they will go back to the depot. So here I will have to use two lower bounds for this version. So consider the convex vertex that is the furthest from the depot, and consider the geodesic, furthest in terms of geodesic distance, because we are dealing with polygon. So consider the distance from a depot to this vertex in geodesic distance. Yeah. So this the claim here is that the optimal solution will be longer than or equal to 2 times this distance, because this is a convex vertex. So at least one endpoint of the k segments have to directly visit that convex vertex and then go back. So this is just from that observation. And then we also have the second lower bound, which says that the optimal solution has to be greater than or equal to the perimeter of P divided by 2k. This is from the same argument as earlier, where we have 2k TSP tours that visit all the convex vertices. And that has to be longer than the TSP tour of one agent. So with these two things, I will approximate it like this. So consider the boundary of P. I will add k minus 1 points on the boundary of P, which together with the depot will perfectly split the boundary of the polygon into k parts of equal length. And then for each additional point, I will draw a geodesic shortest path from the depot to that point. And now I have k polygons, k polygons. So I will just let the segment deal with each of these separately using the previous approximation algorithm. So the perimeter of each of these polygon is at most this much, which is perimeter of P divided by k plus 2 times d max, which is less than or equal to 3 times r. And if we reuse the same approximation earlier, we will have a trail approximation. And that's it. And this is kind of nice because, and it was a surprise to us because we thought that it might have been dependent on k or something, but it's good that it doesn't. And this is the last main result of the problem. So here we have polygon with holes, and we also have a constant factor approximation, and the constant also have 2 digits. So this is the outline of the algorithm. So first we will compute a minimum spanning tree that spans all of the boundaries in the polygon, which means that it touches all of the holes and also the outer boundary of P. So this tree can either have Steiner points or not, doesn't matter. But then we will consider this. The spanning tree together with the boundaries of the holes and the outer boundary of P, together they will create a degenerate simple polygon P prime or a weakly simple polygon. And now we have a simple polygon again, so we can just reapply the previous approximation algorithm. But to be able to prove that this is an approximation, we have to prove 2 things. First, we need to prove that the total perimeter of all of the holes they have to be a lower bound. That had to be the lower bound of the optimal solution. And then we also have to prove that the length of the minimum spanning tree is also a lower bound of the optimal solution for this to work, because the perimeter of P prime depends on these two things. So to prove that, we will consider the following. So consider the trajectories of the two endpoints from the beginning until the end. We have some kind of arrangement of trajectories. So in this arrangement, we will have phases, and a phase can either contain 0 hole, 1 hole, or more than 1 holes. And what I want to prove is that for each of these phases, the total perimeter of all of the holes will never be will be shorter than the perimeter of the phase. So to prove that, I will consider only one phase, so it's easier to see what's going on. So let's consider a phase F in the arrangement, which is drawn in blue here. And this phase has some holes, which is filled with gray ink. And then consider the geodesic, the relative convex holes CH, which is drawn in orange, the relative convex hole of the holes in F. So the claim here is that for the segment to sweep the interior of this relative convex hole CH, the CH has to collapse onto itself at some point and split the set of holes into two subsets, or in other words, it creates at least two pockets, and it split the set of holes in two different pockets. So this is the claim. So why does we have that claim? I will show a simpler example for us to see what's going on. So here we also have the phase F and the relative convex hole CH in orange. So we recall the definition of the phase F. The phase F is made of the trajectories of the two endpoints, right? So to sweep the interior of F, or to sweep the relative convex hole, the endpoints of the segment can never enter the convex hole CH. So to sweep the interior of CH, the segment has to sweep it using the interior points of the segment itself, which is what you are seeing with the A2, B2 position with a red arrow pointing to it. And this kind of leads to a problem. So with the problem, we in the beginning, the two endpoints start at the same location, right? S. And it means that at some point during the schedule, the segments will have a positions where the two endpoints, the entire segment is completely outside of the relative convex hole. But to sweep the relative convex hole, it has to get to a point where the segment is non-trivially intersecting with the relative convex hole. But it means that there has to be a transitioning point where we get from A1, B1, which is completely outside of CH, to A2, B2, which is intersecting with CH. But that is a problem because we have CH is a curve with convex vertices, and the convex vertices of CH, they are supported by the vertices of the holes. So the only way for the segment to get from A1, B1 to A2, B2 is to kind of move or jump over the convex vertices of CH. So this is a problem because the convex vertex, since they are supported by the vertices of the holes, so it means that the segment itself will have to jump over some vertices of some holes, which is impossible because we require that the segment has to stay connected at all time. So in this case, so when the relative convex hull does not collapse onto itself anywhere, it means that it's impossible for the segment to sweep the interior of the relative convex hull. And the only time that it is possible is when the convex vertex of the relative convex hull is supported by a reflex vertex of the face F, as you can see in the figure on the right. But because the face F is the outer boundary of everything here, so when a convex vertex of CH is supported by a reflex vertex of F, it means that CH has to collapse onto itself at that point as well. And it potentially separates the set of holes into two or more subsets. And here's kind of like a demonstration of it. So here we have the relative convex hull in orange. So this is impossible for the segment to sweep. So it has to collapse at some point. And then we will then again apply the same argument, which means that we compute the relative convex hull of the subsets of holes. And then with the same argument again to sweep these new relative convex holes, they have to collapse again and again until every hole has its own pocket. So any questions about this one?
So what's the conclusion?
So the conclusion is because now we have every hole in this own pocket in the relative convex hull. So we know that the perimeter of the hole has to be less than or equal to the perimeter of the pocket, which means that the total perimeter of all of the holes has to be less than or equal to the perimeter of the CH and less than or equal to the perimeter of the face F. And this is the lower bound for one phase of the arrangement of the optimal solution. And that is the lower bound for the perimeter of the holes. So there's also another lower bound that I need to say about the minimum spanning tree. So for each hole, I can create a connection from the hole to the collapsing point. As you can see with the red edge in the figure. So these red edges together with the face F and the arrangement of the two endpoints, these together will create a spanning tree that span all the, not exactly a spanning tree, but it will span all of the holes and the outer boundary of the polygon. And this is also a lower bound because the total length of all of these rest connections will also be less than or equal to the perimeter of F. So now that we have these two lower bounds, the first one is the total perimeter of all the boundaries less than or equal to 4 times opt, and the total length of the minimum spanning tree less than or equal to 4 times opt. We now can say that the perimeter of the weakly simple polygon P prime will be at most this much 12 plus epsilon times opt. We have an epsilon here because we are assuming that we are using the betas for the minimum spanning tree with Steiner points. And finally, reapplying the algorithm for the simple polygon case, we will have a factor of 48 plus epsilon. It is very, very big. So we are trying to improve it right now. But like originally I got something like 108, but like getting here is it's a little bit of work, but like at least we got here.
Where did the epsilon come from?
The epsilon is from computing the minimum spanning tree using a betas.
Oh, I see.
So for a recap, before moving on to other variants of the problem, here's a recap. So for a single segment in a simple polygon, the problem is strongly NP-hard, and we have an 8 approximation algorithm. And for polygon with holes, we have a 48 plus epsilon approximation algorithm. And finally, for the case where we have multiple segments, we have a 12 approximation algorithm.
So, sorry, when you have multiple segments and holes,
that's what we are thinking about.
Okay.
Yeah, that's a work in progress. I think it still applies, but it will need a little bit more work.
So sorry, what phase is? Oh, it looks like everything, right?
Yeah, it could be complicated because I have it has less control. I have less control when there are more segments, but I think it could still work. But there will be something like divided by k somewhere with a lower bound.
Right, because you need to like kind of keep track of which agent you're talking about, then that particular phase within.
Yeah.
Actually.
Also, there's not a clear way for me to kind of like divide it. I'm not sure if computing the minimum symmetry and then I think that's still a good idea, yeah. But like it gets very big. So all right. So that is everything I have to say about the unbreakable segment sweeping version, where you keep the segment inside the polygon at all times. So here are some other variants of the problem. So this is the sweeping the polygon with a breakable segment case. So you need to move this up a little bit. And so here we also have a segment and we want to sweep everything, but now we don't require that the segment is connected all the time, but they can only sweep something if they are connected. That is the requirement. So imagine it's like two robots and they can only sweep or detect something if they see each other. If there's a wall between them, they can still move, but they won't show anything. Yeah. And using the same NP-hardness thing earlier, we can also say that this problem is strongly NP-hard, even if the polygon is simple. And the approximation algorithm still works. But I want to give some analysis about the unbreakable case versus the breakable case. So given a simple polygon P and let TU be the max span of the unbreakable segment and TB be the max span of the breakable segment, then we will have two inequalities. The first one is TB less than or equal to TU, which is trivial because the breakable segment has more flexibility, so it has to be faster. And then we also have the other inequality, which says that TU is less than 2 times TB. So to prove the second inequality, we will consider any sweeping schedule of a breakable segment. So consider any sweeping schedule for the breakable segment. We can classify the schedule into periods of two different types. So the first type is the co-visible period, where the two endpoints of the segment see each other and they sweep something. And then there is also the hidden period where the two segments move around, but they don't see each other, so they don't sweep anything. So for the co-visible periods, we can just let the unbreakable segment do the same thing because they see each other. So for the unbreakable segment, it's fine. But for the hidden period, what we want to do is to convert a schedule of the hidden period of the breakable segment into a schedule that is feasible for the unbreakable segment. But and the time it takes is no longer than twice. So to do that, it takes some case analysis, but the essential idea is that consider the beginning snapshot of the breakable segment and the last snapshot of the breakable segment in any hidden period, and then consider the geodesic shortest path of the two endpoints from the beginning, between the beginning and the end. It will create a polygon, and we simply triangulate this polygon, and then let the unbreakable segment follow this path, this polygon, one triangle by one triangle until the end. So this will create a schedule for the unbreakable segment, but the time will be 2 times as much.
So slightly weird question, but when when these two things coincide,
Yeah.
Do they see the point that they coincide?
Yeah, but I don't think they will ever really sweep anything when they are point, right? They sweep a 1D thing, but
Yeah, so
Yeah.
that kind of doesn't matter.
Yeah.
Yeah, no, I was just concerned because I'm assuming you'll have to like contract it to a point and then move it around, but I don't know if that will cause any issue.
No, in this case we don't need to contract it into a point. We just need to move one triangle by one triangle. So and here's an example to showcase that in the worst case the ratio can get to 2. This is because in this pinwheel, let's consider a unbreakable segment schedule to sweep 2 different pins. The unbreakable segment has to get out of it and then get in to the other pin. Then this tag cut along, but for the breakable segment, it can sort of do this because they don't care about staying inside the polygon, so they can do this. So the time it takes is twice faster. And this analysis breaks down when we deal with polygon with holes. So in the polygon with hole, the ratio can get as bad as ON. So this example kind of showcase that because for a breakable segment, what we need to do is simply to sweep all of these spaces between these horizontal holes. The breakable segments can simply go from the top to the bottom, and this is constant time. But for an unbreakable segment to sweep all of these spaces between the holes, it has to travel in between the spaces, in between these holes, and it has to go around all of these spaces one by one. There's no way around that. And with the low bound that we also had earlier, in the polygon with holes case, we can conclude that in the worst case, which is like this, the ratio between the unbreakable case and the breakable case can get to ON. And this is why we still don't know about the hardness. The problem is NP-hard, but we don't know how hard it is to approximate. So for the breakable segment sweeping in a polygon with holes, we still don't know. And we conjecture that it is actually AB log ABX or something like that, but we don't know yet.
So, sorry. So again, so is there a reason why your holes aren't just rectangles?
Good question. Originally they are rectangles, they all align really perfectly, but like we thought that we want something more general, and there's no degeneracy in in the counter examples. So in the example, so we just make it like that.
I see. So just to show that the hardness doesn't come from degeneration.
Yeah.
There you go.
And finally, this is the last variant of the problem that I will talk about. This is also a work in progress, and this is not exactly sweeping with a line segment, but it's similar enough. So here we have sweeping with a Taut string. So earlier, when we sweep with a segment, the connection between the two endpoints will always be a straight line segment. But in this version, what we sweep with is a geodesic shortest path between the two endpoints. So as you can see in this figure, when the object move from AB to A prime B prime, the string will have to wrap around these two reflex vertices.
But there's no restriction on the length, right?
Yeah, there's still no restriction on that.
So there was an earlier version about geodesics, but there the endpoints have to be on the boundary, right?
That's true. So one of the more they have some restrictions. So one of the restriction is that the two endpoints have to be on the boundary, and I think that is a walkable polygon or something like that, or street polygon.
Mm.
Yeah. So but we don't have that restriction in this
But
anymore.
they still have to start in the same point.
Yeah. So it's just easier for us to analyze, but like I don't think it really matters that much. We might want to have an analysis on the problem where the depot can be anywhere, and yeah, and the two endpoints can also start different locations at some point. So this problem is we don't know exactly how hard it is yet, but like for a skinny polygon, which is just a tree, skinny simple polygon, which is just a tree, we know that it is at least quickly and hard from partition, because as you can see in this figure, we have all the edges going out of S, and then the two endpoints have to divide the work so that they can sweep everything in the amount of time that is the solution of the partition instance. So this is quickly and hard. But this kind of proof, this guy get brought down when we introduce area into the polygon. So we don't know how to prove it for non-zero area polygon yet. And here is a very simple approximation for it. With the beginning from the starting point, we simply let one endpoint of the Taut string go clockwise around the boundary, and the other endpoint go counterclockwise, and they will keep moving as quickly as possible until they sweep everything, this is a 2 approximation. And finally, sweeping with a Taut string, but in polygons with holes. And this is, again, will be strongly NP hard. And the proof is from Hamiltonian path in hexagonal grid graph. I will not bore everyone with the details here, but basically, if we have a hexagonal grid graph, I can create a gadget like this, and then I will kind of attach these two gadgets to a very long horizontal bar, and the Taut string can sweep all the Taut strings begin at the middle of the bar, and then they will divide the work, letting one go to the left and the other go to the right, so that they have to sweep each of the gadget on their own, and then they can sweep it efficiently if they can solve Hamiltonian path in hexagonal grid graph, and that's it. So, and this is the case analysis when they do something else, but it will be very
painful.
Yeah, to talk about. This is I wrote this with, I think it was 6 pages. So, and that is everything I want to talk about today on the problem and the variance. So for the current problems in the future, we want to improve the approximation factor, like I said earlier, there might be a p-task, but like even for the current algorithm, it could have a better factor if we do some different kind of analysis. And then we also want to find the approximation for the breakable segment and the Taut string versions of the problem. And there are also more related variant where, so one of which the agents can have limited fuel, they cannot travel like forever, and then we might have more than 2 endpoints or agents, so they might form some kind of net or 2D shapes and go around sweeping everything with the 2D shapes. And that's everything. Thank you everyone for listening. So